Okay, welcome everybody today. We have Johanna Brunar from Technical University Vienna talk about the source of a smooth digraph. Please, Johanna.
Thank you very much, and thank you for the opportunity to talk here today, or rather tonight in Europe. I'll be talking about directed graphs, as it says in the title, on infinite vertex sets, and in particular on a structural result that yields a hardness criterion for the computational problem induced by such a graph. And in fact, this is the first hardness criterion of this kind. This talk is based on a joint work with Marcin Kozik, Tomasz Nadj, I hope, okay, and Michael Pinska. And this is actually my first online talk since COVID. So if I'm going way too fast, please stop me in between. Since graph coloring falls into the wider class of computational problems called constraint satisfaction problems, I want to first define them quickly, even though most people will probably be very familiar with them, and then state some of the key results on the road to the main theorem, the CSP dichotomy theorem, which will also influence heavily the formulation of the result that I want to talk about. So a relational structure is always a pair consisting of a set A and a family of relations on the set, where the family of corresponding arities of this relation is denoted the signature of a relational structure. And the base set A can be both finite and infinite, and depending on which, we then call the structure a finite or an infinite structure. And well, for the most of this talk, we will only consider relational structures that have only one relation, which is binary. So this is what I mean by a digraph, and seen on the right on this picture. What is now the constraint satisfaction problem induced by such a relational structure? It is the following decision problem, where as an input, we have a structure X of the same signature. So meaning that all of these relational symbols used in the language of A also have an interpretation in X. And we now have to decide whether or not there exists a homomorphism from this input structure X to the template structure A. And the homomorphism is a mapping from the corresponding underlying sets, which respects the relations. So again, if we talk about a digraph, means that if this is a vertex of X and this is a vertex of X that are connected by an edge, then also after the solution homomorphism, I wanted them to be connected by an edge in A. So this is the general problem, constraint satisfaction problems, and many problems can be formulated as such problems. For example, any graph coloring problem. For instance, if we take the graph on 3 vertices, which is complete, then asking whether or not there exists a homomorphism from an input structure X into this graph K3 is the same as asking whether or not a graph is 3 colorable. So of course, this decision problem is NP complete. But as I said before, the template structure does not need to have a finite vertex set. It may also be infinite. For example, if we look at the digraph Q with the order, then which graphs are Q colorable? These are exactly the ones that do not have a cycle. So this CSP is the digraph acyclicity problem. And note that the infinity of the structure is actually needed to model this problem in this way as a constraint satisfaction problem. And maybe one more example too, because the above two examples are just for actual digraphs. The last one is an example where we actually have more than just one relation. So we add to the base set of the integers 0 and 1 as constant relations, and plus and times as ternary relations, and then the CSP of this structure is asking whether or not a given Diophantine equation, so an equation using integer coefficients and plus and times, has an integer solution. So these are all examples of CSPs, and so this CSPs have been studied for a very long time. In fact, since the 70s, but the systematic research began with the formulation of the so-called dichotomy conjecture in the early 90s, where Feder and Vardy conjectured that for a finite template structure A, the corresponding CSP is always either tractable, so solvable in polynomial time, or it is NP complete. And well, it took a whole of 24 years to solve this theorem. And finally, in 2017, two independent proofs by Bulatov and Schuck appeared. And of course, within this time span, lots of results have been obtained. I want to focus on some results on the way of on the way to the proof, which influenced the way that we think about constraint satisfaction problems now. So in fact, this dichotomy theorem was proved for certain subclasses of finite relational structures before it was proved in the entirety in 2017. And it was discovered that very often these complexity dichotomies correspond in a very elegant way with structural dichotomies. So by this I mean that by this I mean statements of the form that either a structure A has a large expressive power in some sense. So, for example, if one can show that somehow, I don't want to formally define all of the concepts here, but what I mean by this is that if a structure somehow constructs a hard problem, then and in such a way that nothing gets lost of the complexity, then this corresponds to the CSP being NP complete. And if it does not have such a large expressive power, then there exists an obvious obstacle to such a thing. So, for example, it could be that there are some kind of symmetries in the structure or polymorphisms, as we will discover later on, that prohibit the structure to construct something, to construct other structures or certain other structures. For example, if we go back to A being just a digraph, then if this digraph might have a loop, and then if it has a loop, then it cannot construct any loopless structure. And note that if it has a loop, then if a digraph has a loop, the corresponding CSP is trivial because you can send everything to the loop. So these structural dichotomies have been obtained for certain subclasses on the way of proving the whole theorem, and I would like to pick two of these results in such a flavor, which I would like to focus on. So, namely, both of them consider just graphs. The first one is a theorem of Helm and Neschetral, already received in the 90s, and it was back then. It was not formulated in this form, but let's use this reformulation so that it fits into the whole frame. So it says that if G is a finite graph and is undirected and non-bipartite, then this structural dichotomy is as follows. Either its PP constructs K3, and subsequently, because the CSP of K3 is NP complete, so is the CSP of this undirected graph G, or it contains a loop, which is why we can also consider this as a so-called loop lemma, because we say either it has this expressive power or the graph must have a loop. But this theorem holds only for undirected graphs, but there is also a similar version in some sense for directed graphs obtained in 2009. Why similar or why translation? So this algebraic length 1, again, I don't want to define this properly, but it can be seen as a generalization of non-bipartiteness for directed graphs. And smooth means that every vertex has both an ingoing and an outgoing edge. And we only work with smooth digraphs, so these assumptions make sense. And in this case, the same conclusion holds. So this is again an instance of a loop lemma, because again, either the structure PP constructs K3 or it has a loop. And right, so these theorems work with graphs, but of course they only work for finite graphs, and we would like to go on and deal with infinite ones. When it comes to infinity, not all graphs of infinite size can be considered, but we need to restrict ourselves to a concept in which such structural dichotomies can be received, at least in principle. And this is the prominent concept of omega categoricity or oligomorphicity, which is very prominent in model theory, of course. And so let me nevertheless define it quickly. So if omega is a subgroup of the automorphism group of a graph G, then the factor graph modulo omega, or modulo the one omega orbit equivalence, has an edge between two orbits, if and only if there exist representatives in every orbit that edge to each other in the original graph. So this is what I mean by the factor graph. And now we say that a subgroup of the automorphism group is oligomorphic if for every k, the action of omega on k tuples of G, it has only finitely many orbits. So this is why this might be translated as an oligomorphic structure being close to finite, because for every k, it has only finitely many distinguishable k orbits. And yes, as an example is again the Q with the order, this digraph that we already had in the beginning. And yeah, so this is the concept in which results can be lifted from finite to infinite, at least in principle. And when trying to lift such results, what we do is because oligomorphicity gives us that every orbit, that we only have finitely many orbits, we can kind of deal with the orbits as we dealt with elements for finite graphs. So the one orbits take the role of elements, and very often, if we translate a result from finite to infinite, we get assumptions or properties in the factor graph rather than the original graph, and these will be named pseudo assumptions or pseudo properties. Let me give you an example of what I mean by lifting finite to infinite. So for example, we had this first structural dichotomy of Hell-Nash before, And now, or actually, so this is a fairly recent result from 2023. It was managed to lift this result to the case of infinite digraphs that are, infinite graphs that are oligomorphic or omega categorical equivalently, in the following sense: if G is smooth and this is oligomorphic and non-bipartite, and the factor graph is symmetric, then we have again a dichotomy. Either on this side we construct something hard, or we get a loop in the factor graph. So before this was a loop in the real graph, now it's just in the factor graph, and such a thing we'll also call a pseudo loop, to sound more fancy. And yeah, so maybe let me remark that before I colored the pseudo loop part in a different color for a reason, because before the loop always implied tractability of the corresponding CSP, but now the pseudo loop does not necessarily have to imply anything like this. But on the other side, this is still purple, so this constructing something hard still gives hardness of the corresponding CSP. And yeah, so in the beginning, I promised a result about digraphs, and this thing, because of this assumption of the factor graph being symmetric, does not give anything about digraphs in general. So we go back to remembering that there was this counterpart for finite templates for directed graphs from 2009. And the question is, can this result also be lifted to the infinite in a similar way, or like to a similar formulation as before? So this would of course be the dream, to get something like this for general directed graphs on infinite sets, or on like general directed omega categorical graphs. But maybe let's not be immodest with our dreams so far, and take back a look on what was done to get the CSP dichotomy theorem. And so a step, or an important step towards receiving this result was a result by Bulatov in 2003, who solved the dichotomy conjecture for the case of conservative templates, so-called conservative templates. And by these, we mean templates where all subsets of the domain sets are contained as unary relations of the relational structure. So in particular, in the CSP, or unions of elements may come up as constraints. Or to formulate this in the language of CSPs, a conservative graph coloring problem, or maybe to some better known as list homomorphisms. List homomorphism problems is the following problem. Again, as an input graph, we get a finite digraph H, but now also we get a mapping L, which goes from the vertex set of the input graph H to the power set of the vertices of G. And now we need to decide whether or not there exists a homomorphism that additionally respects this mapping L. So we could see the vertices of G as colors, and now we assign to every vertex of H an arbitrary list of colors, of allowed colors, to which every vertex may be sent to under resolution. So this is how this can be seen as a graph coloring problem, with additionally restricting the sets of the colors to which every vertex can be sent to. So list homomorphism problems have been studied for many classes of of finite digraphs, but not so much for infinite ones, which is what we want to do now. Again, if the subgroup is oligomorphic, then we consider the 1 orbits of omega, of which there consists only finitely many, to take the role of elements. So now the colors are given by the orbits, the 1 orbits of the graph G, and now unions of 1 orbits may appear as constraints in the constraint satisfaction problem, or in the list homomorphism problem. To formalize this, we for the graph G, we take the K conservative expansion of G with respect to omega to be the relational structure that we obtain if we add to G all unary relations of the form K unions of orbits for every K. And yeah, so now the constraint satisfaction problem of this expansion corresponds exactly to the list homomorphism problem of G. And we now have all the ingredients to finally state our result, namely, if G is a smooth digraph of again algebraic length 1, so this is this generalization of non-bipartiteness for directed graphs, and omega is an oligomorphic subgroup, then we take G hat to be the 2 conservative expansion of G with respect to omega. So again, we expand G by unary relations, but not for every K, but just for K is equal to 2. So we can also use all unions of pairs of orbits as constraints in the constraint satisfaction problem. And we obtained now the structural dichotomy that either G hat, this expansion, has a large expressive power, i.e. PP constructs this graph K3, or it has a pseudoloop with respect to omega. So again, this side of the potato corresponds to hardness in this sense. If G is as before, then this expansion models exactly the list homomorphism problem, and the constructing of K3 now gives us that the list homomorphism problem of G is NP complete. So this is very cool because no such criterion has been known to exist before for infinite digraphs. And maybe you are disappointed that on the left-hand side of this potato, we do not get any computational complexity, but stay with me, because at the end, we'll see that there can actually be also derived something cool out of the existence of a pseudoloop. Yeah, so it was already quite hideous to only state this theorem and to maybe tell you why we would come up with this theorem as a lifting of some results that have been obtained before for finite digraphs, and of results that have been met on the way of proving this big dichotomy theorem. And I, of course, want to spare you from the proof. But what I do want to do is to give you just some insight on the main ideas involved in the proof and the techniques or the new techniques that we used. So, of course, because we work with omega categorical structures, it makes sense to look at factors which are finite, because this is exactly what oligomorphicity gives us. And since we are trying to lift a result from that is known to hold true for finite graphs, one could try to apply techniques that we know to work for finite graphs to such a factor graph, and then lift back these properties that we obtained to the factor to the original graph. So this is like a natural strategy that one could choose. But of course, this will not work for any factor, for any finite factor, because if we factor by an equivalence which is too coarse, then we might lose all the information when passing to this factor, and then we cannot lift anything meaningful up towards the original graph. So the first main goal is to even find a congruence by which it makes sense to factor to be able to lift established techniques in this sense. Omega is kind of the only thing that we know that we are given. So so omega is the building block of everything we want to do, and we know that the factor graph of G of omega is finite. So we want this alpha to be a refinement of omega. So in particular, it could be omega itself, but there are some reasons why omega is not enough in some cases, why we lose too much information when factoring just by omega. But of course, this refinement cannot be too fine. In particular, we don't want to lose that the factor graph is finite, because otherwise, well, we couldn't apply techniques that we know that work for finite graphs. Thirdly, on our wish list of what we want for our alpha to hold true, is that alpha is compatible with omega, right? Again, we know stuff about omega, and we don't want to lose this information when dealing with alpha. And also, this third bullet point of compatibility with omega gives us that we can let the group omega also act on alpha classes. That this makes sense. So this is to make sure that actually all of this is to make sure that alpha is in some sense very well compatible with omega. And then the fourth bullet point makes sure that we have kind of as much information or as much regularity as possible on the factor graph modulo alpha. So we would like to be the edge relation to be a bijection between alpha blocks if we fix any two orbits. So maybe this makes the most sense if I explain it in these pictures that I tried to draw. So here the graph modulo omega consists of 3 blobs, which represent the 1 orbits. And each of these orbits consists of 2 alpha classes, which is always the A and the B. And the edges go as it follows. And now this fourth bullet point of the edge relation being a bijection only means that if this alpha class A0 maps to A1, then it cannot also map to B1, for example. So what would be, how could a factor graph modulo alpha possibly look like for this example? So it starts, if we start with A0 here, then we go to A1 and then to A2, so we just follow the green ones, and then we go to the bottom and B1, B2, and then back to A0. So this is just an example to see how this factor graphs modulo omega and modulo alpha could act within each other. And yeah, so constructing this alpha is the first task that we need to do, and then one could try to do exactly what is written there, to perform proofs in this maybe established ones or maybe new ones in this factor graph, which is finite, and then lift back up the results to the original graph. But of course, this is not easy or will not work in all cases. There are multiple problems that might appear on the way. But I want to focus on one problem or the solution to a problem, because sometimes if you define a set or a relation in a factor in the factor graph G modulo alpha by some formula phi, then the same formula may define a relation in the original graph which also factors to alpha, but it might have less power than the original one. And to overcome this obstacle, we would like to when working in the factor graph modulo alpha and getting some nice relations or some nice sets that we deal with, we really want to blow them up to the original graph. So we lift them by adding, if so this is the relation in the factor graph, and so for example this alpha class here is connected with this alpha class here, and the blow up now is the thing that you might intuitively expect, connecting all points contained in the respective alpha classes on each side. So know that in particular this blow up factors to this relation here, and it's also homomorphically equivalent to it. And with this at our hand, we will be able to prove what we want to prove. So maybe this is just a reminder what we want to say. We want to say that either there is a pseudo loop or there is some constructibility of something hard to get the hard constraints or hard list homomorphism problem. So the proof strategy is to say, assume that that our graph does not have a loop, so this side does not hold, and what is left to do then is to show that that we get this source of hardness, which will be of the form or sigma sigma, where sigma is an equivalence relation on a finite set, and this is the four area relation defined by this formula here, and it is known that such a relation, if you have this OR relation, then this is a source of hardness in the sense of this construct something hard, and so when working in the factor graph, we try to get such an OR relation. So this is good because then we know that the factor graph has this thing, but we're not there yet because we will still need to blow up this relation on a finite set to a relation on the original graph, which is this step here. So either we show that either we are able to define the alpha blow up of such a relation or sigma sigma, which guarantees us hardness, and thus we are able to finish a proof, or we show that if such a relation does not exist, then we can always reduce the problem to a proper subgraph, and it is then left to show that this reduction can only appear in finitely many steps, and after finitely many steps, we need to end with this alpha blow up. Yeah, so the proof consists of many steps, which are, so this digraph here is meant to visualize these steps as good as possible, and for us nothing of this is particularly important, only that the proof is carried out by an induction on the number of alpha blocks, because so we want to reduce, and we want to reduce the alpha blocks. And now you see that in this case distinction, we always end up either with this or sigma sigma relation, which then is the source of hardness, as explained before. So the alpha blow-up of this thing is a source of hardness, or we end up in a green case of reduction here, and we show that we can only, after finitely many steps, we must end up in one of the purple cases. And yes, if we assume that at the beginning that the graph does not have a pseudo loop, and we then show hardness, this finishes the proof of the hardness criterion, of the first hardness criterion for infinite digraphs. Right, and I promised, I have a couple minutes left, I guess. As I promised before, even though the left-hand side of this potato doesn't necessarily give anything about the complexity of the list homomorphism problem, we can still get some nice information out of it. Also, this is nice because it has algebraic consequences, and this is the pan-global algebra seminar. So this maybe also justifies why CSPs can be treated here. Before we managed to relate the complexity of constrained satisfaction problems with the with properties of the underlying relational structure. But there is another side of this correspondence to algebra, which also has some implications in both directions. So formally, to every relational structure, we can assign the algebra, its polymorphism algebra, where a polymorphism, I've used this word before, denoted by pol, is a homomorphism from some power of A to A itself. And then one may ask what identities are satisfied by operations from pol A. So while this might appear as a natural question, why is it sufficient, or why does it make sense to consider this question in the course of CSPs? And this is due to the so-called algebraic approach to CSP. So we go back again on the timeline of proving the CSP dichotomy theorem, and another major step which subsequently involved the whole theory of universal algebra in the study of CSPs was a theorem that said that the complexity of the constraint satisfaction problem for a finite template A is completely determined by the identities that are satisfied by this polymorphism algebra. Maybe let me note here that this is also a reason why oligomorphic structures are the ones that are considered, and also the ones to be considered to lift results from finite to infinite, because these are exactly the ones for which a similar algebraic, or in some sense a similar algebraic approach to CSPs work. Also, there has been formulated a complexity dichotomy for CSPs, for CSPs of oligomorphic structures for a certain subclass of oligomorphic structures, but it remains wide open. Yeah, so this algebraic approach initiated the study of identities, and many times such identities have connection to the loop lemmata, or can be derived by loop lemmata that we discussed before. That this is a very beautiful theorem, or a collection of multiple theorems, which says that implying, or how do we usually get such a result? For example, if we focus on this one, so if we want to prove that the polymorphism algebra satisfies some identity, as for example, this 6 Array-Sigus identity, then the idea is to generate a graph from this identity. And I guess this concept is probably very well known, but just a quick sketch. So we generate a graph where there is an edge between a variable x to the variable y, if and only if they are beneath each other. So in this case, for example, we get this graph here. And now the idea is to say that if the structure does not PP construct everything, so we're not in this case of the potato, then it must have a loop. And then we show that a loop in some generated graph of this corresponds exactly to a polymorphism satisfying the identity that we want. So this is a very well-known technique that has been used to derive many beautiful identities, and for at least for finite structures. But of course, before we didn't have loops, but we had pseudo loops. So what do we get for infinite structures? What do we get out of pseudo loop lemmata? And well, the answer is there is not so much known actually. This result from 2016, this is very cool because it directly generalizes the 6 array pseudo-sigurs. So this exactly this one that we had before for finite templates to infinite ones, where pseudo now means that we have to compose with a unary polymorphism on either side of S. And so this list actually goes on. There are more that are known, and for some, like for the 6 Array-Sigurs, it's known that they have this counterpart. Then for some, we can use, for example, at the bottom, it is known that there do not exist counterparts, meaning that there exists an oligomorphic structure that does not PP construct everything, but does not have pseudo we can use. And then for some, it's open. We don't know whether or not these identities lift to pseudo identities in suitable infinite settings. And now with our theorem, we can spark hope that maybe this 4 array pseudo-sigurs, which has this nice mnemonic of area is equal to rare, might in fact apply to infinite structures as well, because with our result, we can show that if we expand a structure A by these pairs of orbits that we used before with this conservativity notion, then either the expansion PP constructs everything, or the polymorphism clone of the polymorphism algebra of this expansion satisfies this nice identity. So of course this is not done yet, because we need to expand something by orbits, but it's the first theorem the first result in this direction. So yeah, I think I would like to finish by rephrasing the main result in a way that is hopefully more memorable. And yeah, thank you for listening. A graph set forth one day to find a finite thing of any kind. Directed 'twas, yet it was smooth, and at length once still in its youth. With pairs of orbits at his hand, it strived to build things on its land. But when it failed to build K3, a pseudo-loop it had to see.
All right, thank you.